board exams are nearing and it's about time we be fully prepared for that. So today we are going to discuss few such questions which are probable to come in your board examinations from the chapter Magnetic Effects of Electric Current. And we are going to prepare together for our board exams 2024. So let's take a look at the marking schemes in previous year questions. So from the year 2019 to 2023, that are the last 5 years questions, if we look at the marking schemes which starts from 1 mark to that of 5 marks, we can see that in 1 mark we have had 1 question in 2020, 1 question in 2021 and 2 questions in 2023 from this same chapter, which gives us total of 4 questions. And how many marks does that make? 4 marks. And if you can see, in 2 marks questions, we have had 1 question in 2022. So, total number of questions, 1, which are giving us total of 2 marks. Now, if we see the 3 mark question, we have had 1 question last year in 2023. So, again, 1 question from this chapter and that gives us total of 3 marks. Now, let's talk about the 4 marks and 5 marks question, which are going to be more of a case study based question and longer ones. So, that is going to be 1 question in 2021 and 1 question from the year 2022. So, that gives us total 2 questions in last 5 years, giving us a total of 8 marks. Can you see? And what about the 5 marks question? The highest scoring mark question. So, we have had 1 question in 2019 and 1 question in 2020. So, that gives us 2 questions in last 5 years, giving us a total of 10 marks. So, isn't it amazing that from this one chapter, we are able to score so many marks if we prepare for it well. Now, if we can even see that in a graphical form, you might see that every year we have had at least 2 questions from this chapter. And last year, that is 2023, we have had 3 questions in total. So, it makes this chapter much more interesting and much more of a focusable. Now, let's discuss few of the sample questions that we have had in previous years and try to see if we are able to solve them, and let's break it down so that you are able to better prepare for it. So, let's see a question from 2019, which is a long answer question giving 5 marks. So, the question says, what is a solenoid? Draw the pattern of magnetic field lines of a current solenoid and a bar magnet. List 2 distinguishing features between the 2 fields. So, you know what solenoid is. It's an electromagnetic device. So, solenoid is what you have to define what is a solenoid, and then you have to distinguish the magnetic field line of a bar magnet and that of solenoid, and then the 2 distinguishing features between the 2 fields. Now, we all know that electromagnetic induction causes a magnetic field which is not permanent, but for bar magnet, it is always permanent. And what else? The direction. So, the direction of a bar magnet. In the magnetic fields, you will always draw the magnetic lines from north to south. But in case of solenoid, that is the magnetic field generated due to the electromagnetic induction, the field lines direction will differ as per the direction of the flow of electric current, right? So, this is actually pretty much easy. It is the basics of our electromagnetic induction itself. So, it's quite an easy question if you can explain it in proper way. So, this gives you an easy 5 marks, right? Then, let's look at the next question that came in 2020. So, the first question here in 2020 was a very short answer type question carrying 1 mark, and another one that is a long answer carrying 5 marks. So, in 2020, here we can extract at least 6 marks from that question paper. So the first question is, the change in magnetic field lines in a coil is the cause of induced electric current in it. Name the underlying phenomena. Now, if you know the name of the chapter, you will be able to answer the question. It is electromagnetic induction, right? Then, let's look at the second question, which is a long answer. So, here it has 4 parts in it, right? The first question asks, what is electromagnet? Again, this is the most basic thing that you have to learn from this chapter. What is an electromagnet? And if you look at the questions which we will be discussing later, you will see this question repeating a lot, because this is the basic of this entire chapter. So keep in mind to understand and learn the actual electromagnetic phenomena and how the electromagnet works, and then list any 2 uses. So we have had the discussion about how many instruments in today's day and age uses electromagnet. We have seen the big cranes which are used for lifting heavy metal items using electromagnet. Then the mics, speakers, everything works on the electromagnetic principles, right? So now the second question. Draw a label diagram to show how an electromagnetic. Now the second question. Draw a label diagram to show how an electromagnet is made. So you have to draw a diagram. Now we all know how electromagnet is made. You need one coil carrying electric current and a soft iron core, and around that you have to helically wound the electric current carrying coil, right? So this is how you make an electromagnet. So you can definitely draw a simple diagram showing a wire carrying electric current in a certain direction which is wound around a central soft iron rod, right? So this is easy. You have to just draw a simple diagram. Then the third question, state the purpose of soft iron core used in making an electromagnet. I am sure that you have known about the permeability of the soft iron, which is why we use it to create electromagnet, and we will discuss this in much detail in later slides. Then list 2 ways of increasing the strength of an electromagnet if the material of electromagnet is fixed. So we have fixed the material. Now what is variable? What else is electromagnetism depend on? The strength of the electric current. If you increase the electric current, then also the strength of the electromagnet increases, right? So either you change the number of coils of the electric wire which is wound around the soft iron, or you can change the material of the core, or you can increase the strength of the electric current, right? So in 3 ways you can do that. But now here we have already fixed the material of the electromagnet. So there are just 2 more ways by which you can increase the strength of the electromagnet, right? Now let's go to the year 2020. From there we have had one question for 1 mark, which is a very short answer type question. So let's look at the question. Why do 2 magnetic field lines not intersect each other? It's a very interesting question. Or what is an electromagnet? Again, if you can see, this question is repeated, which is just the basic of this chapter. And why do 2 magnetic field lines not intersect with each other? Think about it. It's very simple. Just imagine if they are intersecting at one point, then what would be the direction of the magnetic line? And if you place magnetic compass needle in that point, where will the needle face? Won't that be confused? It will, right? So that is the reason why we can say that the 2 magnetic field lines do not intersect. It is always parallel to each other. Now let's move on to another question which is of 4 marks. That is a case-based question. Now here what you have to do is you have to study the following paragraph and then try to answer the questions from 1 to 5. Okay, so let's study the case first. Hans Christian Ørsted, 1777 to 1851, observed that a compass suffers a deflection when placed near a metal wire carrying an electric current. This discovery gave the first evidence of a connection between electric and magnetic phenomena. André Ampère, 1775 to 1836, grasped the significance of Ørsted's discovery. He carried out a large experiment to explore the relationship between current electricity and magnetism. On the basis of experiments, he hypothesized that all magnetic phenomena are due to circulated electric currents. Later on, many devices such as electromagnets, electric motors, microphones, electric generators, etc. were developed on the basis of magnetic phenomena. So this is a very informative piece of paragraph. Now let's try to answer the questions from 1 to 5. So let's look at the first question. A magnetic needle is a or an isolated north pole pivoted at its center of mass, isolated south pole pivoted at its center of mass, ordinary needle made of soft iron and pivoted at its center of mass, small bar magnet pivoted at its center of mass. So obviously, unless and until it's a small magnet, it will not align with the north and south pole of the Earth's magnetic field, right? So it is going to be D. Small bar magnet pivoted at its center of mass. Then, second question. A freely suspended magnet always rests in geographically north and south direction because the Earth has 2 poles. The Earth behaves as a huge magnet. The magnetic north pole of the Earth's magnet is located very close to the south pole. The magnetic south pole of Earth's magnet is located very close to its south pole. We have heard this millions of times that Earth behaves as a giant magnet and where its north pole is located and where its magnetic north pole is located. So I am sure you will be able to answer this question. Think about it. Then, so moving on to the next question. When a current flows through a straight conductor, a magnetic field is produced around it. Consider the following statement about this field. And the options are: the direction of the magnetic field of a current carrying straight conductor is determined by right hand thumb rule. Do you know which one is the right hand thumb rule? Like this. What is this? This is the straight conductor and these fingers represent the magnetic field lines. Right? Then second, a charged body placed in this field experiences a force whose direction is given by Fleming's left hand rule. And the third one, the magnetic field lines around a current carrying straight conductor are in the form of concentric circle with the conductor as the center. So this statement basically is actually defining the right hand thumb rule, right? So the options here we have to select which are the statements which are true for this answer. So now we can say for A it is number 1 only, B number 3 only, C 1 and 2 and D 1 and 3. So like we said that the option number 3 is basically just the definition of the right hand thumb rule. So the correct answer would be 1 and 3 because this is saying exactly the same thing, right? Now let's move on to the next question. The strength of magnetic field of a current carrying solenoid is A. minimum at its end, uniform inside it at all points, maximum at its center, 0 at its center. Another easy question carrying 1 mark. right? So, see from 2021, this long answer, if you break it down as a case-based question example, you can easily score 5 marks from it. Now, let's look at another question, that is the last or fifth question. Which one of the following particles would not experience a force while moving perpendicular to a uniform magnetic field? A neutron, an alpha particle, an electron, or a proton? Again, it is, you have to answer all the 5 questions in this case-based example. So, you will know this and you will be able to score 5 marks in total. Now, let's try to see the questions from 2022. Name and state the rule to determine the direction of force experienced by a current carrying straight conductor placed in a uniform magnetic field which is perpendicular to it. Now, we will be also trying to solve this question later. This is a short answer carrying 2 marks. So, if you are able to answer this question, you will straight up get 2 marks. So, the second question is, an alpha particle while passing through a magnetic field gets projected towards north. In which direction will an electron project when it passes through the same magnetic field? Now, if you remember the left hand rule, can you see this? What does that prove? What is this? The force. This is the magnetic field and it is the electric current, right? So, from this, what do you determine? Let's see. Now, let's move on to the next question. A student fixes a sheet of white paper on a drawing board using some adhesive material. Okay. She places a bar magnet in the center of it. So, she places a bar magnet in the center of a sheet and sprinkles some iron fillings uniformly around the bar magnet using a salt sprinkler. On tapping the board gently, she observes that the iron fillings have arranged themselves in particular pattern. Okay, so this is what is going to happen. Magnet attracts the small iron particles, but it will attract in a certain pattern. So, what pattern is that? Draw a diagram to show this pattern of iron filling. So, you will have to draw the magnetic lines, and the direction of magnetic lines is from north to south direction, and you will be able, you know that the lines will be much concentrated towards the center of the magnet, and as you go away from the magnet, the lines are much farther away. So, in the same way, you will have to draw the magnetic lines representing the scattering or distribution of iron fillings around the bar magnet. So, this is how you will attempt the first A part of it. Then second, B is, draw the magnetic field lines of a bar magnet showing the poles of the bar magnet as well as the direction of magnetic lines. Again, we have already answered. So, if you have considered one direction as north pole and the other one as south pole, the direction of the field lines will be from north pole towards south pole. So, you will be showing the direction with the help of an arrow that the magnetic field lines are moving from north pole to south pole. Okay. C. C has 2 parts, that is 1 and 2. So, 1 is, how is the direction of the magnetic field at a point determined using the magnetic field lines? Why do magnetic field lines not cross each other? And then second is, how are the magnetic field lines of a bar magnet drawn using a small compass needle? Draw one magnetic field line each on both sides of the magnet. Okay, so again, we know how to draw magnetic field lines, and using, instead of using the iron fillings, how you can draw the magnetic field lines with the help of a magnetic compass. So, you keep placing the magnetic compass, and in whichever direction the north pole is facing, you keep drawing the north pole, and as you move towards any point, there you place the point wherever the needle is facing. Okay, so with the help of that, by placing the compass at different points, you trace out all the points and the magnetic lines on it, right? How is the direction of the magnetic field at a point determined using the field lines? So, again, we know that by using the magnetic compass, you will be able to determine the direction of the magnetic field line, and we have always seen that the direction of the magnetic field line is from north to south. So again, by answering these questions, you are able to score 4 marks easy. Now, last year's question. Okay, so this brings us to our last year question. This is a MCQ type question carrying 1 mark each. So the question is, the resultant magnetic field at point P situated midway between two parallel wires placed horizontally, each carrying a steady current I is, so here you can see the diagram. Here A in the same direction as the current in the wires, B in the vertically upward direction, C 0 in the vertically downward direction. So what we are trying to say here is that the magnetic field at point P, this is point P as you can see, and it is situated midway between two parallel wires. So these are the two parallel wires and it is placed horizontally, and each is carrying the current I, and in the direction, this is the direction, right? So then what will be the magnetic field at point P? So will it be in the same direction as the current in the wire? No, right? Because we have seen from the right hand thumb rule and with the help of the left hand rule that the direction of the current and the magnetic field lines are perpendicular, right? So if it is the direction of the current, then this cannot be the direction of the magnetic field as well. It has to be the perpendicular to it. So it is the A option is definitely not the one. Second, in the vertically upward direction, is it going to be like this? Vertically upward direction? Is it going to be 0 or in the vertically downward direction? So where will it be? So it can be either B or D. It cannot be 0 here, right? Because the direction is in this side. Now, since it is in this direction, it is going to be like this, right? It is going to be in concentric circle. So it has to be, how is it going to be? It is in the vertically downward direction, right? Now, let's move on to another question, which is assertion and reasoning type question carrying 1 mark. So the assertion statement here is, the strength of the magnetic field produced at the center of a current carrying circular coil increases on increasing the number of turns in it. And the reason that is given is, the current in each circular turn has the same direction and the magnetic field due to each turn, then just adds up. Okay, so this is the reason. Now, here you have to select options given here, that is both A and R are true and R is the correct explanation of A. Both A and R are true, but R is not the correct explanation. A is true, but R is false. A is false, but R is true. So you have to select one of the 4 alternatives for this particular assertion and reason. So the assertion says, the strength of the magnetic field produced at the center of a current carrying circular coil increases on increasing the number of turns in it. Is it true? Yes, it is. The reason is, the current in each circular turn has the same direction and the magnetic field due to each turn then just adds up. So both assertion and reason are correct. So we will go with A. Both A and R are true and R is the correct explanation of A, right? Now let's move on to the next question. Here, state the rule used to find the force acting on a current carrying conductor placed in magnetic field. Given below are 3 diagrams showing the entry of an electron in a magnetic field. Identify the case in which the force will be 1. Maximum, 2. minimum respectively, and give reasons for your answers. So you can see 3 diagrams here, and here in each of the situation you will have to identify in which case the force will be maximum and minimum respectively, and then you have to give your reasons, and you will be giving reasons based on which rule? It is the left hand rule. right? And this type of question, this long answer type question carries 3 marks. Now, let's move on to the next long answer, again carrying 3 marks. Okay, so here, draw the pattern of magnetic field lines of a current carrying solenoid, a bar magnet. So, we have already discussed what solenoid is. It's a coil which is tightly packed in a helix and a current is passing through it, and there is no soft magnetic core or soft iron core in it, right? So, here you have to draw the pattern of magnetic field lines that is carrying in the solenoid and then a bar magnet. If you remember, this is a repetitive question, right? We have already discussed that how there is a distinguishing feature between the magnetic field lines of a solenoid and that of a bar magnet. So, accordingly, you will have to draw the pattern of magnetic lines for the solenoid and a bar magnet. Second is, list 2 distinguishing features between the 2 fields. That too we have already discussed. So, if you can see that by understanding and correctly figuring out the concept behind it, you will be able to score so many marks because this question has been repeating, right? Now, let's try to solve few previously asked questions which are carrying 5 marks. These are long answers. So, this was asked in the year 2020. The question here has 4 parts. A is, what is an electromagnet? List any 2 uses. B, draw a label diagram to show how an electromagnet is made. C, state the purpose of the soft iron core used in making an electromagnet. And D, list 2 ways of increasing the strength of an electromagnet if the material of the electromagnet is fixed. So, by answering this question, we will be able to clear out a lot of concepts which will be helpful in answering many questions asked from this chapter. So, let's see the solution. So, for A, what is an electromagnet? List any 2 uses. An electromagnet is made by passing current through a coil that is wound around a piece of soft iron, right? Among the many electrical devices that use electromagnets are the electric bell, telephone, telegraph, radio, loudspeaker and so on. So, all these devices are used so much in today's day and age, and all of them uses electromagnets. Heavy iron masses are lifted by electromagnets. The heavy iron masses that are lifted using those big cranes are also using electromagnets. An electromagnet consists of a coil wound around an iron piece and connected to a battery. Why connected to a battery? Obviously to provide a source of electric current. Now, next is draw a label diagram to show how an electromagnet is made. Okay, so we will try to draw a diagram here. As we described or we defined electromagnet, there is an electric wire which is wound around a soft iron piece and connected to a battery for the source of electric current, right? So, this is how we can make an electromagnet. This is the simple diagram representing how electromagnets are made. Now, next is state the purpose of soft iron core used in making an electromagnet, right? So, we had already discussed it that it has to do something with the permeability. So, what about it? Let's see. So, soft iron, it is high permeability, allows the magnetic flux from the primary coil to be fully linked to secondary coil. So, if you remember the diagram, it is wound around a soft iron core, and because of the permeability, it allows the magnetic flux from the primary coil to be fully linked to the secondary coil. And the soft iron is used to make electromagnets because the soft iron has good or high magnetic properties. So, we are trying to create magnetic field out of the electric current flow. So because of that, we use soft iron. First of all, it has high permeability to let the magnetic flux pass through, and it has high magnetic properties. So that is why it makes it a very good candidate for making a electromagnet. It can provide a strong magnet. So ultimately we want to make a strong magnet, right? Now the last one. List 2 ways of increasing the strength of an electromagnet if the material of the electromagnet is fixed. So let's assume we have fixed the material of the electromagnet, that is our soft iron. Now how can we increase the strength of the electric magnet? So there are two methods to improve the electromagnet strength if we keep the material of the electromagnet fixed. So first is increasing the coil's number of turns. So by increasing the number of turns the coil is wound around the core or the material which is used in the center, we can increase the strength of the electromagnet. Second, by increasing the amount of current. If we increase the amount of current, then also we can increase the strength of the electromagnet. Now let's move on to the next question, which was asked in 2021, carrying 1 mark. Again, it is a very basic question and you must know the answer to it. Why do two magnetic field lines not intersect each other? That is a very, very important question. We have already tried to answer this question. So let's see what the answer is. And the next is, what is an electromagnet? Again, a repetitive one if you have noticed, right? So the solution is, each point in a magnetic field has a unique direction, right? So every point where you place your magnetic compass, it is going to show a particular direction of the magnetic field, right? So each point in a magnetic field has a unique direction associated with it. If lines intersect, there would be multiple directions at the point, right? So if there are 2-3 lines intersecting, each would be showing a different direction, correct? Which is simply not possible, right? Imagine a compass placed at that point where 2-3 lines are intersecting. What will happen? It would be confused trying to point in 2 directions at once, right? So if there are multiple directions, the magnetic compass would go crazy. It will just keep deflecting from here to there, isn't it? So that is why it is not at all possible. So every point has only one single unique direction towards which the magnetic lines are pointing. Okay. Now, what is an electromagnet? Now we know that what electromagnet is. Electromagnet is made by electric wire carrying electric current wound around a soft iron core, right, and connected to the battery to provide the source of electric current. And this is how the magnetic field lines are going to be in case of an electromagnet. So, an electromagnet is a kind of magnet in which an electric current generates the magnetic field. Electromagnets usually consist of wire wound into a coil. A current through the wire creates a magnetic field that is concentrated in the hole, denoting the center of the coil. And if you place iron or any metal in the center, then it would create a magnetic field through that and it will act as a magnet, right? Now, name and state the rule to determine the direction of force experienced by a current carrying straight conductor placed in a uniform magnetic field which is perpendicular to it. And second is, an alpha particle while passing through a magnetic field gets projected towards north. In which direction will an electron project when it passes through the same magnetic field? Now this was asked in year 2022 and 2 marks is given for this question. Now this is another easy and interesting question which is going to get you 2 marks straight. Okay, so let's look at it. So the solution would be, for the first question, the rule that determines the direction of the force experienced by a current carrying straight conductor placed in a uniform magnetic field perpendicular to it is called Fleming's left-hand rule, right? Which I already showed. It is like this. Okay, so the force experienced by a charged particle moving through a magnetic field is given by Lorentz force equation, which includes the particle's charge. What does that mean then? This means that the direction of the force depends on the sign of the charge. So now here the alpha particle was projected north. This tells us that the direction of the magnetic field and the current flow due to the moving charge combine to produce a northward force on the positively charged alpha particle, right? So because of this Lorentz force equation, we can determine the direction of the positively charged alpha particle, right? Now, when an electron with a negative charge enters the same magnetic field, the combination of the field and the current flow will produce a force in the opposite direction as dictated by Lorentz force equation again here. Therefore, the electron will be projected southward, right? So, because we know that the Lorentz force equation gives us the direction of the force. Now, here we have seen that the alpha particles, while passing through a magnetic field, gets projected towards north. So, obviously, if it is projecting in the north direction, the left hand rule says that the alpha particle will not therefore have the force in the same direction, but it will be in the opposite direction. So, the opposite charges experience opposite force in the same magnetic field. So, by using the right hand rule or Lorentz force equation, we can determine the specific direction of force for each charge. So, if we know the direction of the charge, we are also able to determine in which direction the force would be, right? So, I hope all these questions are going to be very helpful in your coming board exams, and I hope that this chapter is absolutely clear in your mind. As you can see that so many questions have come in it, and I'm sure you will do absolutely brilliant. All the best. Thank you.